All right, in this video, let's take a look at Kepler's laws. We're going to focus on the third law, but a quick review of his first and second laws. First law was the law of ellipses, which basically just stated that planets actually orbit elliptically around the sun, not necessarily perfectly circular. So that means at some point, they're closer to the sun than they are at others. It's kind of flattened out. So this distance would be less than this distance, and the sun would be at one of the focuses. So planets actually undergo elliptical orbits. And the second law related to that was the equal time equal area law. And this deduces from the properties of an ellipse. So as they get closer, they actually speed up, so their velocity increases. As they're farther away, their velocity decreases based upon that radial change and the forces. So they're going to move a greater distance in a less time here than they will when they're farther away here. But that over the same time intervals, these areas will be equal. So that's law 2, is equal time, equal area for an elliptical orbit. Now law 3 is one we focus on the most. And this relates what's common for satellites around the same object. So let's take the sun as our object, and let's take two planets. We'll take Earth, and we'll take Mars. Both orbiting around the sun in mostly spherical or circular, but somewhat elongated elliptical orbits. All that means is that when we talk about the speed of a planet in orbit, it's not always constant. It might be higher and lower at certain points. And we're talking about the average when we talk about like the period of rotation. So that we're talking about the average. 365 days is the average amount of time it takes the Earth to rotate around the sun. It might be moving faster and slower depending on how close it is to the sun, but that's the mean value. So now if we have these two objects, the Earth will be moving at a greater speed than Mars because it's closer in, has a lower orbital radius. So we can measure that orbital radius. So let's call this, I know R of Earth we use a lot for just the radius of the Earth itself. But for this purposes, it's the orbital radius of the Earth. And then we have the orbital radius of Mars. And that's greater. And so what Kepler was able to realize is something we touched on already. And that is, they're both circular motion due to the force of gravity. So if you model this, this will be the mass of the satellite times the mass of the sun, the satellite being any of the planets, over their orbital radius squared. And this is a centripetal force always pointing towards the center. So that force is providing a centripetal acceleration, mv squared over r. And this is the same r. The r for the circular path is the same r as the center-to-center distance of the masses in the gravity equation. And this is the satellite, the object that's accelerating. We notice it's independent of the mass of the satellite. We've already seen that. But if we go a little bit further, and break this down into its smallest components, okay? We know the orbital speed, or the linear speed of an orbit, is just 2 pi the radius over the period. Okay, so and if we simplify this, we'll square this, so 4 pi squared r squared over t squared equals g mass of the sun over r. And then let's get all the like variables to one side. More specifically, not just, well, with the r, the like variables, so this becomes r cubed. But let's get all the constants to one side. So what are the variables that are going to be constant no matter what satellite it is, no matter what planet it is? So no matter what planet it is, the gravitational constant doesn't change, the mass of the sun doesn't change, 4 pi squared doesn't change. So if I bring the 4 pi squared over to the other side by dividing by 4 pi squared, what I see is for any given satellite around a certain object, in this case the sun. The ratio of the cube of their orbital radius to the square of their period is constant. So, which is remarkable because it allows us to make predictions about the distance of planets away from their sun, or the distance of stars away from the center of their galaxy that they're orbiting, by just measuring their period. So, for example, let's say the period and distance to the sun for the Earth is known. If I measure the period of Mars, I can calculate then the radius of Mars just by knowing its period. Because for all satellites in orbit around an object, around a given object, for all satellites, this ratio of the cube of their orbital radius, let's call this for planet 1, to the period squared, is equal to the same ratio for all other satellites. So we can use this expression as a new equation for any two satellites orbiting around the same sun. And that's Kepler's third law. So his genius was in realizing that this is constant for any satellite around a given object, such as the sun. And so therefore, the ratio of the cube of the orbital radius to the square of the period will be constant. And that's Kepler's third law.